Going to be talking about rather abstract theoretical physics ideas. And as most of you know, theoretical physics is no laughing matter. So I'm at a serious disadvantage. I think I have several other disadvantages in that one thing I learned when writing my book was actually the introduction was the hardest part, because one thing that makes describing what we're doing very difficult is that even the words, just getting across what the terms are that define the questions we're asking, is very difficult. So I'm going to try to give you a flavor of what we're doing in the course of these 20 minutes, but it's hard to give the full picture. The second reason that it's hard compared to many of the speakers here, I think, is that there are absolutely no practical applications of this work that I'm aware of. That is a question everyone wants to know the answer to. But on the bright side, you could have said the same thing about Einstein. When he wrote his theory of general relativity, he certainly didn't think that 80 years later that they were going to be using it in GPS to help make GPS systems work properly. So I can't say that I can harness the force of gravity yet, but there could be applications, who knows. But right now there aren't. And the third reason I'm at a slight disadvantage is I have a cold, so I hope you can hear me for the rest of the time. Okay, so my book is called Warp Passages. So a lot of people ask why it's called Warp Passages. So there's several reasons. One, as we're going to see, is that the kind of work we're doing actually deals with the warped geometry of space-time. Einstein introduced the idea that geometry and gravity are connected, and curved space embodies gravity. And in fact, in this particular case that we're going to look at, it's curved in a very particular way, which we call warped. So that's where the word comes from. There's a couple of other reasons. One was that this was my first book, so I was sort of having a little bit of play on words there. Warped passages describing my writing. And a third reason is that I think it's important to know that when we do physics, or when you're as a reader or whatever, you're learning physics, it's not always a direct route. Not everyone follows the same line of reasoning. And in fact, in a lot of the work that I won't have time to describe, but in much of the work, we come across ideas accidentally. It's a lot of ideas flowing in from different directions, and how someone reaches a particular point can be very different. So in that sense, it's also a warped passage. But I also use passage as a dimension because there is really no word for the extra dimensions, as we'll see. Okay. So I just want to give some general overview, which is that I do particle physics. I was trained as a particle physicist. And particle physics, we're told, deals with the most basic structure of matter, the most basic building blocks, and nature's most fundamental laws. And what we do is we keep trying to probe shorter and shorter distance scales and understand more about the universe and the way it works. But one really fascinating aspect of particle physics is that it does overlap with many other areas of physics, and in particular cosmology, describing how the universe evolves, has traded back and forth ideas with particle physics quite a bit. And it also, in terms of understanding the theoretical laws, we've extrapolated far beyond what we can see for sure today, and ideas like string theory, which I'll mention a little bit more about later, have come into play. And so really abstract theoretical ideas that we want to connect to our universe are also there. So we have some basic things about the world we'd like to understand, we have some basic things on large scales that we'd like to understand, and we have some basic theoretical consistency things that we'd like to understand. So since this is the Ideas Conference, it seemed appropriate to ask, how do you get ideas in this? How do you make advances in this highly theoretical discipline? And it's really, as I said, it's a warp passage. It's not one direct route. But I think one thing that's important for us is to connect to experiments wherever possible. That's not always possible, because sometimes we're talking about distances beyond which we can observe yet, and we're just hypothesizing about what's there based on theoretical arguments. But there are experiments, and at the very end I'll tell you about one really important one, that will help us probe beyond what we know today. As I mentioned, you look for theoretical inconsistencies. If you have two theories that clash, that was one of the reasons that string theory came about. We have quantum mechanics that applies at short distance scales. We have general relativity theory of gravity that applies on large distance scales. But it turns out that there is a theoretical inconsistency if we look at very short distances, 10 to the minus 33 centimeters, far beyond what we're going to test experimentally today. But nonetheless, the fact that there is any regime is clear there's a theoretical problem, and it's clear there should be a theory beyond what we know. So that's another reason way we can go beyond what we know. And also, this is really overlapping them, but also interplay with cosmology, looking around at the universe on large scales, and the back and forth there has also taught us some things. So a lot of people are confused about the work that I'm doing because I'm really sort of in between. I'm trying to combine together these two approaches. If you think of string theory as sort of being the top of a mountain, and so if you're a string theorist, you have a theory. It's not fully fleshed out, but you have a theory that you think defines the world, and you're going to try to derive what are the consequences of this theory for the world at the scales that we see. Particle physicists and model builders a lot of the time come from lower energy scales. They're talking about building up from what we know. There are also theoretical inconsistencies at lower scales, scales where we can make observations with experiments. And so we're trying to find a route based on those ideas. And so I do what's called what I call model building. It's generally known as model building, which is something like adventure travel through theories and possibilities for our world. We're trying to connect together these two routes because what we can do is take ideas that come out of string theory and try to see what their consequences could be for problems that we can actually experimentally test. And a lot of the time, the physicists will divide into two classes, but right now we're converging more. And the danger, of course, of dividing into two categories is if you're at the bottom, as anybody who's climbed a mountain knows, it's a lot of hard work, and if no one tells you where the trailhead is, you could get into trouble. So you want to make sure that you're going the right way. But if you're at the top, you have a similar problem, and it's even more dangerous because, as has happened to me at least sometimes, you can end up at the top of a cliff and have no way down. So really what you want is for these two schools to talk to each other to get some new ideas that can lead to progress. So in the course of doing this work, we ended up studying extra dimensions of space. So basically, it came about in my research in attempts to explain phenomena we see in our world. But the idea of extra dimensions has received a lot more prominence because string theory has extra dimensions. So it means that if string theory is right, the question isn't where are the dimensions, are the dimensions there? The question is where are they and why haven't we seen them? So let me just spend a minute saying what extra dimensions of space are, because this is a very confusing concept, and it's probably not one that I'm going to be able to fully explain here. In my book, I have many ways of looking at extra dimensions, but let's just focus for the moment on just extra dimensions of space and what we mean. So I think all of us are familiar with 3 dimensions of space. If you're not, you probably are in the wrong talk. So we have left, right, forward, backward, up, down. But what are we talking about when we talk about another dimension of space? Well, the reason we run into trouble is because we have no way, it's really hard to picture those extra dimensions. We are not physiologically designed to see extra dimensions. But we can use some of the tools that we use, for example, to make paintings, to try to picture what's going on in a higher dimensional world on a lower dimensional surface. And there's many tools you can look at, slices, projections, or whatever. But if we wanted to try to picture it, which is very difficult, we can at least use an analogy. So Edwin A. Abbott in the late 19th century had a very clever idea. He said, well, it's very hard for us in a 3-dimensional world to imagine 4 dimensions, but this would be just like the situation if we lived, say, on a tabletop, on a 2-dimensional world. So if you had a square, he called it a square because he's Edwin A. Abbott, who was the narrator. So he had a square that lived on a tabletop. And what would that square see in terms of the world? Well, they only experienced 2 dimensions. So how would they be aware, how could they see anything about the 3-dimensional world? So one way you might see it is suppose something passed through from the 3-dimensional world. Remember, the square is just stuck on the tabletop and doesn't directly see out to the 3rd dimension. What would that square see? Well, the square would see a series of disks that grew in size and then shrunk in size. So you see a disk getting bigger and bigger and then getting smaller and smaller and eventually gone. And that's to say that there is some interaction with the 3rd dimension, even if you're not directly perceiving it. And of course, if there is energy, energy can flow on or off that dimension. So there can be consequences of these extra dimensions, even if we're not directly perceiving them in any way, with any of our senses at this point. So, but why think about this idea of extra dimensions if we haven't seen them? What is the motivation? Well, as I mentioned before, one of the chief motivations is string theory. These dimensions are there in a string theoretical world. But there's even if you don't trust string theory, and many people don't yet, there's still reasons to think about this. I mean, more generally, there really is nothing in the laws of physics that we know of that tells us there have to be 3 dimensions of space. For example, Einstein's theory of general relativity, which of course is our theory of gravity, is a major advance. It works for any number of dimensions. It doesn't single out 3 dimensions of space. So it's worth asking, taking off where he left off and asking, what are the consequences if there are extra dimensions? That's the only way we're going to know the answer of whether those dimensions are there. But the most important reason, I think, in some ways, is that there really are problems that have baffled physicists for years. And I'd say for about 30 years, we've had the standard model of particle physics, which describes the known ingredients of matter and how they interact, the forces through which they interact. The problem is there's still some puzzles left in that theory. So it's been extremely well tested, but there are puzzles about questions of mass, how particles acquire mass, and also questions about the weakness of gravity, which was mentioned in the introduction and which I'll come back to. So these are really stiff theoretical puzzles. They're not just, oh, gee whiz, we can't do it. It seems that the theory is almost inconsistent. It seems like there's huge fudge that you have to put in the theory to make it work. So people have tried very hard in the context of 3 spatial dimensions to solve these problems. And there are problems, but they're almost as fudged as the original thing. So it's not clear that we found the right answer. And given that we've searched really hard in the context of 3 dimensions, it makes sense to look to broaden our scope and look in the context of higher dimensions, especially since they might be there. And as I'll try to tell you, we have actually found a pretty compelling explanation in the context of extra dimensions. So since I'm not going to have time to tell you everything, let me just tell you a sampling of this sort of gee whiz kind of, or science fiction-y sounding ideas that we now know is possible, but in the context of physics. This isn't just stuff I'm making up. It doesn't mean that, I should be clear, it doesn't mean we know these things exist in the universe. We know that they are theoretically possible, and we can study them through our theories, and actually testing for them is a major challenge ahead. But one thing we find is that there could be, in some sense, multiverses, parallel worlds. I don't mean parallel worlds in the sense that some people think of it. They think of another world where we're happily existing, except doing something slightly different. We're all out skateboarding instead of sitting in this conference. I mean parallel worlds in the sense of really a different universe where you could have fundamentally different chemistry, fundamentally different ingredients, and that could only interact with us very weakly through gravity or even not at all. There can be new connections among physical observables, like this weakness of gravity problem that I've mentioned too. And also, again, we found really fascinating things. By studying this, we found that there could be infinite dimensions of extra-dimensional space that we don't see. And that has to do with this warped space-time geometry. And in fact, it can be so warped that the fact that we observe 3 spatial dimensions could be just a local phenomenon. That is to say, it could be just an accident of our location that we're experiencing 3 spatial dimensions. It could be that elsewhere you experience many more. So these are really genuinely new theoretical developments that were not known since Einstein introduced relativity and since the idea of extra dimensions was introduced in 1919 in the context of physics. Okay, so I've mentioned why we think about extra dimensions at all. Why are we thinking about dimensions now? Well, I've mentioned string theory and Einstein's theory of gravity. And also, I think it's important to recognize, and that was said in the introduction, that every time we look at smaller or larger distance scales, and we really have found qualitatively new phenomena. The structure, the operation of quantum mechanics at the level of an atom is very different than Newton's laws at a classical level. When you go inside and look at short distances, you can find things are very different than what you see naively. Your intuition can fail. And we don't know. Maybe extra dimensions will be another such phenomena. It's certainly something that I would be very interested to find out. But one other ingredient that has really changed the way we study extra dimensions is this ingredient called brains. And again, this is a 20-minute talk, so I can only say a couple of words. But one thing that has changed is that string theory made a big advance in the 1990s and found that it's not just the theory of fundamental strings. So string theory is based on the premise that particles, the fundamental ingredients of our world, are nothing other than oscillation modes of fundamental oscillating strings, hence the name string theory. But in the 1990s, it was realized that the string are not the only ingredients in string theory. There could actually be these other ingredients called brains. So brains is B-R-A-N-E, and it's short for membrane. It's not a membrane, but it's motivated by the word membrane. Because what these brains are their lower dimensional surfaces in a higher dimensional space. And when I say surface, I'm saying a generalized version of surface. That surface could be three-dimensional in a higher dimensional space. So if you have these brains, you can distinguish the directions on the brain and the directions orthogonal to the brain, perpendicular to the brain. So there can be things that live on this brain that travel only on the surface of the brain or only on the interior of the brain, but don't go out into the extra dimensions. And this has given rise to a lot of new ideas about what happens in extra dimensional space, as you might imagine, because if not everything is experienced in the extra dimensions, it's much less constrained and there are many more possibilities. So as I said, brains can trap most particles and forces. And I'm going to just skip through because we're running out of time. So what we can have is we can have something that's now known as a brain world. And a lot of the new ideas about extra dimensions are about these brain worlds. So in these brain worlds, what we have are the ingredients of our world, say all the forces we know about, electromagnetism, he's holding a magnet, people, the things that we're made of, atoms, galaxies, whatever, can all live on the surface of the brain. But what makes these brain worlds interesting is that not everything can be confined in a brain. If everything was confined, for example, on a brain that only had 3 spatial dimensions, that wouldn't be very interesting. Why wouldn't it be interesting? Because then everything would just look like a 3-dimensional world, and as a physicist, I wouldn't care. But the reason we care is because we know that fundamentally gravity has to be connected to the extra dimensions. Gravity cannot be stuck on a brain. And there's many ways of seeing that. You can see it in string theory because it's associated with a closed string, but more fundamentally, you can just see that Einstein said that gravity is sensitive to energy, and that energy can be anywhere, not just on a brain. And furthermore, gravity is connected to the geometry of space-time. So again, gravity has to know about the whole universe. So that says that even if we have this brain world picture and we are stuck on a brain, that we nonetheless interact with the extra-dimensional world, making it of interest to us. And this exotic idea of multiverses is also connected to the idea that there can be brain. If there can be one brain in the universe, why can't there be many more? There's certainly no reason, once we accept the idea of a brain world, that there can't be other brains. But if all the ingredients of our world, including the forces, electromagnetism, the weak and strong nuclear forces, are stuck on our brain, that means if there is anything on those other brains, it's going to be different. It's going to be fundamentally different ingredients, not just quarks and leptons like the electron that we know about, and it's not going to be the forces that we know about. So there really are many, many possibilities for what we can have in this brain world picture. And of course, I'm not going to have time to tell you about all of them, although I do describe many of the different possibilities in my book, for those of you who are interested. But let me just say, the sampling of what we've learned in the context of these brain worlds are new ways to hide dimensions. Before, it was thought, since the 1920s, it was thought that the only way to hide extra dimensions, the only reason we don't see them is because they're very tiny and they're just invisible to us because they're so small. As I alluded to earlier, we now know that extra dimensions can unfurl infinitely far and still be hidden if space-time is warped in a way that we can describe. There's a new way to explain the weakness of gravity. Fundamentally, the idea is very simple. If we have extra dimensions, there's no reason that gravity cannot be strong somewhere else but weak where we are. And we actually have an explanation in warp space-time of why gravity should be strong elsewhere and weak where we are. And as I also alluded to earlier, a new concept of our place in the universe. So the idea for gravity being very weak is rather simple, but it's a little technical to derive, of course, but what we have is the idea that gravity gets very highly concentrated in the vicinity of one brain, which we call the gravity brain. And it's very weak in the other vicinity. And what I've plotted is the graviton probability function, which just tells us basically how likely we are to find gravity in any particular region. I have 1 minute left, so what I want to point out, I'm not going to be able to explain this in detail, but one thing that really is interesting about this is that if this theory is right, there actually are experimental implications. And those are called KK particles, Kaluza-Klein particles, named after the physicists who first started thinking about extra dimensions. But the idea is that there would be extra heavy particles that would carry, that would actually have heavier masses because they travel in the extra dimensions. And basically, because E equals mc squared, as all of us have heard, if you go to higher energies, you can study heavier particles. And the Large Hadron Collider at CERN, which is going to be an accelerator that's going to collide together protons, converting mass and energy into energy, which will then get converted back to mass, can actually create these particles. So you can actually collide together the proton beams, make these particles, and that would be extremely exciting because we really could have experimental evidence of extra dimensions. So I guess since I have 4 seconds left, I will just close there. But I will also mention